Greetings and salutations, everybody. This is Jacob. Okay, so how do we go about solving this problem? Seems complicated. You might be tempted to use a binomial distribution formula, just like we did in the previous probability puzzle, if you've seen that one. But we can't use a binomial formula because the probability changes as the order in which the pills are removed changes. The binomial formula implies that the probabilities stay the same no matter what the order in which the pills are removed, which isn't the case here. We're going to have to brute force this problem specifically and add up all the individual probabilities. I'll show you what I mean exactly by this. So first of all, let's find the number of different orders in which the pills can be removed. So since each time we remove a whole pill, a half pill replaces it in the jar, except when we remove the last whole pill. This one is not replaced because the problem is asking for the number of half pills in the jar at the moment the last whole pill is removed. So when we draw out 6 whole pills, 5 half pills are created. Makes sense? And so since we want 4 half pills to be in there when we remove the last whole pill, and we only have to draw out 1 half pill, correct? So 6 whole pills and 1 half pill, 7 pills in total. So we use the formula of distinguishable permutations. That is, the number of permutations of n objects, r of one type, and n minus r of another type. So n equals 7, the total draws, r equals 6, the whole pills, and n minus r equals 1, half pill. And this formula is the same formula as the combinations formula, which is 7 factorial over 6 factorial times 1 factorial. And this is 7. So now let's list out the different orders in which we can draw the pills one by one. Since it's only 7, it's easy to do this. So we have the first case, WWWWWH. But we eliminate this case because we draw out all the whole pills first, and we're left with 5 half pills in there, not 4. And moving on, we have the next case, whole pill, whole pill, whole pill, whole pill, whole pill, half pill, whole pill. Then whole pill, whole pill, whole pill, whole pill, half pill, whole pill, whole pill. Then whole pill, half pill, whole pill, whole pill. Then whole pill, half pill, whole pill, whole pill, whole pill, whole pill. Then whole pill, half pill, whole pill, whole pill, whole pill, whole pill, whole pill. And last but not least, half pill, whole pill, and then all the whole pills. But this case is eliminated because there's no half pills in there initially. So in practice, we're left with only 5 different orders in which the pills can be drawn. So that's easier for us to do. So we have to actually calculate all these cases differently because their probabilities differ, like I said earlier. So let's start with the first case, or the first legitimate case. So we'll calculate the probability of it. So the probability of this order, we just multiply all the individual drawings, their probabilities. So the probability of drawing the first whole pill is 1, obviously, since the jar initially only has whole pills. The probability of drawing the second whole pill is 5 over 6, since there are 5 whole pills left out of a total of 6 pills. And the probability of drawing the third whole pill is 4 out of 6. The probability of drawing the fourth is 3 out of 6, 1 over 2. The fifth is 2 out of 6, 1 over 3. Now we get to the half pill. The probability of drawing a half pill here is 5 over 6. Since 5 half pills are in there, because we've already moved 5 whole pills so far, and 6 pills are in there in total. So now we're down to the last whole pill. So since we removed a half pill isn't replaced. So now we have 5 pills in there total. So the probability of removing the whole pill is 1 over 5. And so we multiply all these individual drawings, and we get probability of this case is, as you see here, which is 50 over 3,240, which is roughly 0.015. And we apply the same reasoning for all the other scenarios, and we get the probabilities of each of these scenarios, as you see here. The probabilities are a little bit different for each one. The probability decreases as the half pill is drawn more and more towards the beginning. Now that we have these probabilities as individual cases, to get the total probability that we're left with 4 half pills in the jar, we just add these individual probabilities, and we end up with approximately 6%. And that's your answer. 6%. Seems like an intuitive answer, if you ask me, my friends. So now let's answer the second question. What is the expected number of half pills left in the jar after the last whole pill has been removed? $1 million question. So let's start out by explaining what the expected number is. The expected number is just the average result that we end up with if we repeat the experiment enough times. This concept is called mathematical expectation. This is the formula for it. F of x is a probability distribution, whether it's continuous or discrete. The weight is the weight function. In this case, since 1/2 pill replaces a whole pill, and the weight equals 1. So having stated that, now let's proceed to answer this question. Let's start out by asking what is the expected number of half pills left after we've removed one whole pill? It's 0, correct? Since the last whole pill isn't replaced and the jar initially has 0 half pills, so 0 is the correct answer. What about 2? After we've removed the second whole pill, then the expected number is the expected number after removing one whole pill plus a probability of removing the second whole pill, which is 0 plus 5/6, which is 5/6. What about the third whole pill? Again, it's the expected number of half pills in the jar after we've removed 2 whole pills, plus the probability of removing the third whole pill, which is 5/6 plus 2/3, which is 1.5 half pills. And so we use this reasoning for all the 6 whole pills, and we get expected number of half pills after we've removed all 6 whole pills, 5/6 plus 2/3 plus 1/2 plus 1/3 plus 1/6. And that is 2.5 half pills is expected to be in the jar. And that's your answer. So yeah, I hope you liked this problem, my friends. This one was neither here nor there. Not too difficult, not too easy. Just right, as Goldilocks would say. I was a bit overdue a probability puzzle, so I decided to do one today. After the monstrosity of last time, my friends, that was something else. Let me know if you found this one difficult. Not that I have a strict schedule of the types of problems that I make videos of. It's more like a loose balance. I like to balance the types of problems loosely, as to not have, for example, 10 physics problems and just one logic problem. You know what I mean. So yeah, you know the drill, my friends. Destroy those buttons like there's no tomorrow. There's more goodies on the way, my friends. Lateral thinking, logic, set theory, algebra, geometry, probability, calculus, physics, differential equations, chess, combinatorics will be the main areas of focus on this channel. Take care, my friends. God bless you all, and I'll see you in the next video. Bye-bye.